Welcome back. We are now going to talk about AC bridges. And in our last class, just a quick reminder, we have seen the series and parallel equivalence of a practical capacitor or an inductor. That was necessary because that will make AC bridges often very easy to deal with. Okay. Now, so we are going to talk about AC bridges. So, this is a generalization of Wheatstone bridge. So, what do we have in a Wheatstone bridge? We have 4 resistances connected in like this. So, in case of Wheatstone bridge, all these boxes they denote actually some resistance. I am drawing them as boxes on purpose, and then we apply some voltage across 2 opposite terminals, and we measure the current between the other 2 terminals. So, this is the detector, this is the source. Okay. This is the structure of a Wheatstone bridge. In case of an AC bridge, we just need a AC source, of course. So, this becomes an AC source. This detector should also be a suitable one which will work for AC voltages or currents, and this impedance, this boxes can now be any impedance other than or even including resistance. So, they are not necessarily pure resistances, they can be inductance, they can be capacitance, they can be anything, okay, or some combination of that like L, C, anything, they can be in general anything, L or C, any combination of them. So, in general, so we will call them as Z. Let me call this as Z1, Z2, Z3 and Z4, and once again we can find the balance condition. What is balance condition? What do we mean by balance condition and null condition? It is the situation when no current flows through this detector. And that is only possible if the potential here and here are exactly same, both in magnitude as well as in phase, because now we are talking about AC. Okay. In case of DC, there is no phase associated with voltage, but now we are talking about AC voltages. So, we need the magnitude and phase of these 2 voltages to be exactly same, assuming this is a AC pure sinusoidal supply and all voltage are and currents are purely sinusoidal and with same frequency, no harmonics present. Okay. So, then the balance condition once again will mean like Wheatstone bridge is that Z1 by Z2 is equal to Z3 by Z4. This is what we have seen for Wheatstone bridge as well. There we write as R1 by R2 equal to R3 by R4. Now, it is general admittance as general impedance. Okay. And how do we obtain this balance condition? Once again, it's very simple to derive. So, let us take this point as reference, call this voltage as V. Now, V is a phasor. Okay. Now, V is a phasor, and then this voltage will also be V, because this is the reference 0 volt. Therefore, at balance, if no current is flowing here through the detector, okay, so no current goes out from here or no current goes out or in from here. So, the potential at this point can be found, call this V1 and V2. We can write V2 using potential divider rule as V divided by Z2 plus Z4 multiplied by Z4. This Z4, this is potential divider rule, and similarly V1 will be V divided by Z1 plus Z3 multiplied by Z3. Okay, and these two should be equal if no current is flowing through this. If this current is 0, therefore, V1 equal to V2 will imply these two terms same. So, you can write Z4 divided by Z2 plus Z4. This is this term. V you can cancel from here and here. So, and this is Z3 by Z1 plus Z3. Now, from this it is easy to write. Now, subtract 1, you will get Z2 by Z4 is same as Z1 by Z3, okay, or Z1 by Z2 is same as Z3 by Z4. Now, this is not just one equation, although it looks like one equation, it is actually not one equation, it is two equations. Why? Because all these numbers are complex numbers. These are complex impedances Z1, Z2, Z3, Z4 are all complex impedances. Okay, like R plus j omega L or R plus 1 over j omega C or so many other things. So, these are all complex numbers, and one complex equation means two real equations. How? We have to equate the real part of this with the real part of this and the imaginary part of this and the imaginary part of this. That is one way of thinking it. Or you think of this term being represented as in its magnitude and angle form. This also can be represented in its magnitude and angle form. Then the magnitude of left hand side should be same as the magnitude of right hand side, and the angle of left hand side should be same as the angle of right hand side. So, we can write this as, so if Z1, we write this Z1 as the magnitude with the angle theta 1. Similarly, Z2 equals its magnitude with angle theta 2. These are complex numbers, and so on Z3, Z4. Therefore, we can put these values in this balance equation and write Z1 magnitude with the angle theta 1 divided by Z2 magnitude with the angle theta 2 same as Z this is 3 magnitude with angle theta 3, and okay. So, from this we can write two conditions. One, the magnitude of the left hand side, which is same as the magnitude of the right hand side, and the angle of the left hand side we can write this as theta 1 minus theta 2, okay, because this is a ratio. So, the angle will be theta 1 minus theta 2. So, this will be same as theta 3 minus theta 4, okay, or you can write this equivalently as theta 1 plus theta 4 is same as theta 3 plus theta 2. So, the angle of opposite sides 1 and 4, the angle of this and the angle of this, and the sum of these two angles should be same. So, the sum of opposite angles should be same. Theta 1 plus theta 4 should be same as theta 3 plus theta 2. This is one condition and this is another condition. Now, this is the balance condition, and this equation we can write, this is the balance condition in ratio form. Because we are taking the ratio of two adjacent sides Z1 by Z2 and the other two adjacent sides Z3 by Z4, they are equal. We can also write the same balance equation as by taking the product Z1 Z4 should be same as Z2 Z3 and this condition okay. So, this is the product form of the balance equation. Same equation we are writing it in two different forms. Why? Because sometimes it's, as we progress we will see it is easy to write things in this form, and sometimes it will be easy to write equation in this form. Okay. So, just a small note that same equation, same condition can be written in either form. We can take the ratio of adjacent sides, or we can take the product of opposite sides. The ratio of adjacent sides should be equal, that is the ratio form of the equation, and the product of opposite sides should be equal, that is the product form of the equation. Okay. Now, before we progress, a small quiz, small question for you. If I give you this bridge, say I have a resistance, another resistance, here I have a inductor, here I have a capacitor, okay, and you can put the detector and the source. Call this R1, call this R2, L3, C4. The question is, what is the balance condition? For this bridge? You may pause the video at this moment and try to come up with the answer, Or I can pose the question in a different way. Is this bridge balanceable at all? I mean, can this bridge be balanced? Once again, you may think yourself by pausing the video, or I discuss the answer. The answer is no. Why? Because if we want to balance this bridge, we will definitely need that two conditions satisfied, that the one is the magnitude, ratio of magnitudes like R1 by R2, and it's the magnitude of this impedance and the magnitude of this impedance, their ratio, they should be equal. Another condition is the angle condition, which says the angle of opposite sides, they should their sum should be equal. Now, what is the angle here? The angle for a pure resistance is 0 degree. The angle, so the angle here is 0 degree, the angle here is again 0 degree. What will be the impedance angle for a pure inductor? It will be 90 degree, and for this it will be minus 90 degree. Now, if you take the sum of opposite sides 0 and minus 90, it is minus 90, and here it is 0 plus plus 90 is plus 90. So, 0 degree plus minus 90 degree is never equal to 0 degree plus 90 degree. Okay. So, therefore, this bridge can never be balanced. So, through this we learn one fact, that all bridges are not necessarily balanceable. That means, with any choice of R1, R2, L3 and C4, with whatever value you choose, you can never get a situation where these two voltages are equal and no current flows through the detector. Okay. Now, what do we use bridges for? Bridges are used to measure some unknown impedance. Okay. So, bridges are used to measure on some unknown impedance Okay. So, we put the unknown impedance in one branch, in one branch of the bridge or one side of the bridge. Other three sides are known and variable. Not necessarily all three sides are variable, but maybe one or two sides are variable. So, other sides are known, variable, and then we vary the other three sides, find the situation where we get a null in the detector, and then from the balance equation Z1 by Z2 same as Z3 by Z4, we can find the value of the unknown impedance, because three impedances are known, one is unknown. So, we can find the unknown one. Now, in general, our task in electrical measurement will be, given an unknown impedance, to configure or design a bridge with one unknown, of course, and three known branches, three known and variable branches, to find the balance condition. This is our task. Configure a bridge with one unknown and three knowns and find the balance condition, and then from the balance equation find the unknown value. Now, when we are configuring or designing a bridge, we must keep it in mind that all configurations are not balanceable. Like one we have seen here, this is a non-balanceable bridge. So, we should never design or configure a bridge which is not balanceable. Okay? So, this is one thing to learn. Now onwards we will learn a lot of different bridges, but the approach you should take is that never try to memorize those bridges or the names of those bridges, that okay, this is Maxwell bridge. A Maxwell bridge has one inductor, one capacitor, they should be in the opposite branches, and the capacitor should be in parallel with the resistance, the inductor should be parallel with the resistance. Never remember these things. Never remember that this bridge is called Maxwell bridge, this bridge is called Hay bridge, Wayne's bridge, Carey-Foster bridge. Never ever try to remember this. Try to understand how these engineers or scientists have designed these bridges, how Maxwell have designed his bridges, how Hay or Wayne have designed their bridges. If you understand how to do that, you don't have to remember any bridge, and even in exam you need not reproduce from memory any bridge. You can design your own bridge. Always the goal is there will be one unknown impedance which you want to measure, three other branches are known and at our control. Those are variable and known. We will choose those three bridges such that the measurement becomes easy. Okay? So, let us write while studying AC bridge, one side is always unknown, is the unknown. Other three sides are our choices. Other three sides are our choices, and the way to choose is keeping two factors in mind. Number one, the balance equation should be easy. I mean, we would like to have a easy looking balance equation. Another factor is convergence should be easy. Okay. So, we will understand both these factors with the help of examples. So, now onwards we will only take examples and solve problems. Okay. So, example, let us start with very simple one. So, we have an unknown but pure means almost pure capacitor. We want to measure it using a bridge. Okay. So, we have to configure or design, whatever you call, design a bridge. Basically, we have to choose what to put on the four arms. Now, a bridge means always these 4 arms. Now one of them will be the unknown, the capacitor. So of course we can put the unknown one in any branch you like, anywhere you like, put the unknown one. This is Cx, and this is nearly pure, so no parallel or series resistance we are putting here. Now the question is what to put in the other 3 branches. That is our task, and we will do it in a way whichever is easiest. And I feel the easiest way could be this: just put a variable capacitor here, this is variable C1, put a resistance R2 variable, put a resistance R3, this can also be variable. Okay. So, I think this is easiest, or you can choose whatever you think easiest. Okay. You might have chosen to put this capacitor here and this resistance here. Okay. I mean, it's in a way symmetric. And why I am saying this is easiest? So, the balance equation what can we write? We can write, say, the impedance of this, which is 1 over j omega C1 divided by the impedance of this, okay, adjacent sides, 1 over j omega Cx should be equal to R2 by R3, and from this we can write, so this j omega cancels, we write now Cx goes up, C1 down is same as R2 by R3, which implies Cx is same as R2 by R3 C1. So simple, okay, just one equation, real equation, no imaginary part, this is so simple. Okay. So, this is the idea, make a bridge which is simple, which is easy. Okay. Now, this is example 1. Now, let me take another example, example 2. Say we have a practical leaky capacitor, so which we can always model as we have seen like this, Cp and Rp. So, we have this unknown. So, we have to measure Cp equal to how much and Rp is equal to how much. This is the task, and for that we have to design a bridge, and we will design a bridge which is simple and easy. That is the idea. Okay. So, once again we start by drawing a bridge which has 4 arms. Okay. And I am not drawing the source and the detector. Okay. It is always there. It is understood that the source and detector is there, but for simplicity I am not drawing it. Another reason I am not drawing the source and the detector, because the balance condition does not depend on the position of source and detector. Okay. So, I mean, I can have Z1, Z2, Z3, Z4. The balance condition is Z1 by Z2 equal to Z3 by Z4 is true no matter whether the detector is here and the source is here, or the detector is here and the source is here. The balance condition will be same. Convince yourself. Okay. Since the balance condition will be same, we are not putting the detector and the source to keep the diagram clean. Okay. Okay. Now, task is to measure this. Now, to measure this, okay, let me put this unknown in one branch, okay, or okay, let me call it x, x for unknown. Okay, here also x, x, x for unknown. Okay, so let me put the unknown again, say in one branch. So I put it here. So this is Rx, Cx, and now the question is what to put here, what to put here, what to put here. That is our choice. Okay. Now we will do it once again in a way which is easiest and which is balanceable. That is also important. We have seen some bridges are not balanceable. For example, if we do it like this, say we put two resistances and here we put RC parallel combination, this is not balanceable. Why? Because the angle condition says the angle of this and this, the sum of these two angles should be sum of these two angles. Now, the angle here is 0 degree, angle here is 0 degree. So, the sum of 0 degree and 0 degree is definitely 0 degree. The angle of this impedance RC parallel combination will be somewhere between 0 and minus 90. This will also be between 0 and minus 90. Say this is around minus 45, we do not know, it will be somewhere between 0 and minus 90. This will also be between 0 and minus 90, say minus 45. This, so their sum is minus 90 and this two sum is 90, they cannot be equal. So, this bridge is not balanceable. Okay? So, we cannot balance this bridge. So, this bridge is wrong, but let us try by say swapping these two like this, put the resistance here and the RC parallel combination here, okay, call it C1 R1, R3 and R4. Now, let us check quickly, is the angle criteria satisfied? Yes, it can be satisfied, because this angle is between 0 and minus 90, this is 0. So, their sum is between 0 and minus 90. Similarly, sum of these two will again be between 0 and minus 90. So, by a proper choice of C1 and R1, we can get this balance. Okay. So, this is I think the easiest bridge we can use. So, what will be the balance condition? And this should be easy, that is what we want and simple. Okay. So, the balance condition, let us write it this way. So, the impedance of this divided by the impedance of this. So, which will be, let me call this impedance Z1, this Z2, R3, R4. So, Z1 by R3 should be same as Z2 by R4. Okay. Now, sometimes it may be easy to write the equation in terms of admittance instead of impedance. So, let us rather write this as 1 over y 1. What is y 1? It is 1 over z 1. This is the admittance. Then R 3 should be equal to y 2 by R 4, and then we can write y 1. Now, y 1 will be same as, okay, let me first write it this way, y 1 R 3 same as y 2 R 4, and then I write in place of y 1, this will be 1 by R 1 plus j omega c 1, this should be equal to, okay, whole multiplied by R 3. In place of y 2 we can write 1 by R x plus j omega c x. Okay. So, this is multiplied by R 4. Observe that it is easier to deal with admittance because these branches and these branches are in parallel. Okay. And when things are in parallel, admittance get added. When things are in series, impedance get added. So, when dealing with parallel combination, it becomes easier to write things in the form of admittance. Okay. So, small note, it is easier to write admittance when elements are in parallel. Similarly, if the elements are in series, it becomes easier to deal in terms of impedance. Okay. Now, from this you see it is very easy to equate the real part of left side to the real part of right side, and similarly the imaginary part of left and right sides. So, we can write the real part, which will be R 3 by R 1 same as R 4 by R x, and the imaginary part, so j omega c 1 R 3 j omega c x R x, c x R 4, sorry. Okay. Now, this j omega cancels. So, we have c 1 R 3. Okay. Let us bring the R 4 here. So, this is equal to c x, and R x from this is easy. It is R 4 R 1 by R 3. Okay. So, what we observe? We observe that the balance equation is easy if we take this bridge. So, once again, the goal is to deal with bridges which has an easy balance equation, and the important thing that we learn is that if the elements are in parallel, it is easy to deal with the admittance, and then just equate the imaginary part and equate the real part. That is all. It is as simple as that. Okay. Now, I will tell you a fact, a interesting fact. Most often we can design simple bridges. Simple means whose balance equation is easy and simple to derive. Most often we can design simple bridges using the idea of a product bridge or a ratio bridge. So, this is a new thing we are going to learn, what is a product bridge and what is a ratio bridge. They are suppose I have this bridge. If I write the impedances as Z1, Z2, Z3, Z4 and the corresponding admittances are 1 over Y1, 1 over Y2. So, these are admittances, 1 over Y4, 1 over Y3. Okay. Same bridge I am drawing here. So, the admittances are Y1, Y2, Y3, Y4. They are nothing but 1 over Z4, 1 over Z2, 1 over Z3, 1 over Z1. So, by notation Z impedance and Y admittance. Okay. Now, the balance condition for this bridge you can write in this way. Say, let me write it as Z2 by Z1 same as Z4 by Z3. Ratio of any adjacent side, you can take it in any way. Z1 by Z3 is same as Z2 by Z4 or Z4 by 3 same as 2 by 1. So, the ratio of adjacent sides, similar ratios of adjacent sides should be equal. Okay. And then if I call one of them, say this is the unknown, here also let this be the unknown. Okay. So, then we can write the unknown Z2 as Z1 multiplied by Z4 by Z3. This is the unknown in terms of the known ones. Now, on this side we can again write the balance equation in terms of admittance instead of impedance, like we can write say let us write it first this way. Z2 will once again will be same as Z1 Z4 okay, by Z3. This is true, this is the same equation. Okay. But this I can now write in terms of the admittance using this Y3 is 1 over Z3. Now, if we choose, so in on this side we can choose this factor Z4 by Z3 to be a pure real or pure imaginary number. Okay. Then Z2 and Z1 will be a complex number, Z1 complex, Z2 complex, but Z4 and Z3 we can choose them to be purely real or purely imaginary. If we choose them both to be purely real, then the ratio Z4 by Z3 is a real constant. Okay? And then the balance equation will have only Z2 complex, Z1 complex. Thus, we can equate the real part of Z2 with the real part of Z1 multiplied by this factor, and similarly real imaginary part of Z2 to the imaginary part of Z1 multiplied by this factor. Okay. So, if we choose this, okay, then Z4 by Z3 is a pure real or imaginary, pure real or pure imaginary number, call it k, and then we can write Z2 is equal to Z1 multiplied by k. If k is real, then real of Z2 will be same as real of Z1 and imaginary of Z2 will be same as imaginary of Z1. Okay. So, this is a pure real number. So, balance equations becomes so simple. Okay. Balance equation becomes so simple if we do it in this way, or if k is imaginary, then of course real, okay, this multiplied by k, then real of Z2 will be imaginary of Z1 multiplied by k, and real of Z2, imaginary of Z2 will be same as real of Z1 multiplied by k. Okay. So, the point is the balance equation becomes easy. Is simple and easy. Okay. Therefore, so our goal was one unknown will be given and 3 known arms to be designed. We can design it in this way, keeping this equation in mind. Okay. So, we will take, if this is unknown, we can take Z4 and Z3, 2 side by side adjacent arms to be purely real or purely imaginary, like pure resistance or pure capacitance, okay, or one pure resistance, one pure capacitance, that is also fine. But do not mix like series combination of RL, parallel combination of RC. No, then the balance equation will be difficult. Okay, that is what we want to avoid. We will, so this is the way to design it. This is an easy way to design it. Then we do not have to remember anything if we just do it this way, and this we will call the ratio bridge. This form of the bridge we will call the ratio bridge. Why? Because the ratio of 2 adjacent arms Z4 by Z3, we will choose it to be pure real or pure imaginary number. Okay. I think it will be more clear if we just take an example, and the example we have already seen is this. Okay. This was the unknown, okay, and these 3 are our choices. Branch 1, 3 and 4 was our choice. We have chosen R3 and R4 to be pure real numbers. See, this is pure real numbers, and therefore, this ratio R3 by R4 is a pure real number, and that is why the balance equation was so easy. Okay. So, this is This was an example of a ratio bridge. So this is a ratio bridge. Where two adjacent sides are chosen to be pure. Now, similarly, another type of bridge that we can design or configure is keeping this equation in mind. Z2 is equal to Z1 Z4 multiplied by Y3. Now, we can choose any guess. Z1 Z4, this factor to be pure real or pure imaginary. Okay. If we do so, then this factor Z1 Z4 is equal to K is a pure real or imaginary number, is purely real or imaginary, and if K is real, then of course we can write the real of Z2 same as K multiplied by real of Y3. Okay, from this real of this will be same as real of Y3, and here real of, not real, imaginary of Z2 will be same as K multiplied by imaginary of Y3. Okay. And similarly, if K is imaginary, then you can write imaginary of Z2 is equal to K times real of Y3 and real of Z2 K times imaginary of Y3. The balance equation becomes easy. Once again, the bridge or the balance equation becomes simple. Okay. So, these are the two forms of bridge. This we will call the ratio bridge, this we will call a product bridge. These are the two forms of the bridge that we can often use to design bridges. Okay. Now, we will take an example with which this idea will be quite clear, I guess. So, now we have to measure say a practical or lossy inductor, which we can always denote as a series combination of LS RS. Okay. So, we have to measure this one and we have to design the bridge. Now, let us take let us draw this bridge. So, let us first put this unknown one in any branch you like, any branch. I like this branch. Okay. So, this is unknown, LS RS, you can call L X also, X for unknown. So, this is unknown and I want to design a simple bridge. Okay. The goal is to design a simple bridge. And let us use ratio form or ratio bridge. This is my choice. I want to use a ratio bridge. What I can do? I can just do this. Put a known L1 R1 variable. Put a variable R 1, 2, 3 and R 4 variable. Okay. So then let us see how easy the balance equation is. Okay, so we will write this as Ls, say this divided by this. So j omega Ls. So let us write it this way directly from here. Z2 is equal to Z1 multiplied by Z4 by Z3. Okay, so let us start from there. Z2, this is 2. This is Z1, Z2, Z3, Z4. Z2 is same as Z1 multiplied by, so this is 4 by 1, 4 by 3, 2 by 1, 4 by 3, yes. So now here we can write Ls j omega plus Rs. Here we write Z1 same as L1 j omega plus R1 multiplied by, this is R4 by R3, and from this we can directly write Rs, this unknown. So this is the real part of the right hand side will be R1 multiplied by R4 by R3. And similarly, imaginary part will be j omega Ls, j omega L1 multiplied by R4 by R3. So j omega cancels from both sides. So I write Ls same as L1 by R4 by R3. So you see, it took me just 2 lines, 2 lines to write and derive the balance equation, because I have designed the bridge in a simple way. So once again, the point is to design the bridge in a simple way so that the balance equation becomes easy to derive. I just can look at the bridge and also can sometimes write the bridge in one line. Okay. Now let us take a last example in this class. To measure a lossy inductor, but we cannot or we do not have a standard means known standard variable inductor. Okay. So in the previous problem we used a variable standard means known here inductor. So L1 R1 was known and variable that was used. Now we put a constraint that we do not have a variable standard inductor, that is the constraint. We do not have it in the lab. How do we do it? This is not a funny question, this is a practical question, because standard inductors are difficult to prepare, difficult to have. We will talk about later why. Right now you accept that it is difficult to have a standard variable inductor. Okay. So this is a more challenging question, let us do it. So this is the bridge with 4 arms, and let me put once again the unknown one first, anywhere you like. So this is unknown put it anywhere you like among the 4 branches, and now the task is to find what they should be. Okay. Now, we cannot use a variable LR as we did here, that is not available. So, what can we do? We have to use can we use just only resistance? Simple question. Can we use only resistance like this? No. We cannot, because then the angle condition is not satisfied, because angle of here this is 0, angle of this is 0. So, this plus this is 0, but this angle is something between 0 and 90, this is 0. So, their sum is between 0 and 90. So, angle condition is not satisfied. So, this is not possible. So, we cannot balance it using resistance only. Okay, so, what can we do? We cannot use inductor. Can we use capacitor? Because capacitor gives non-zero angle, resistance gives only 0 angle. So, can we use capacitor? Let us try. Let us try by putting a capacitor here. Let me keep R and R here, and let me try to put a capacitor. Okay, so now will this help? No, once again this will not help. Why? Because sum of these 2 angles is between 0 and 90, okay, but sum of these 2 angle is minus 90. We can never get a balance. So, this is also not helpful, but now we can try another thing. Let us try this. Let us put the capacitor here and a resistance here. Then these 2 angles, this plus this is 0, and this is minus 90, this is plus something, and minus plus can cancel each other and become 0. So, these 2 can become 0. Okay, for that if this is not purely 90, so this cannot be purely 90. So, I may use this. Okay. Now, this is between 0 and 90 positive, this is between 0 and minus 90 negative, and if I adjust these 2, then I can make this the angle of this equal to this. So, they will cancel each other and sum up to 0, and these 2 they sum up to 0. So, this is possible. Okay, it is good. So, this is the easy bridge, and this is also, you observe, is going to be a product bridge, because you see the sum of 2 opposite arms here are chosen to be pure. Call this R1, 2, 3, R4. So, you see according to our condition, you see sum of 2 opposite arms, we have chosen them to be purely real, these 2 R and R. Okay, so, this is going to be a product bridge. Okay. So, that is what we have seen. I mean, product bridge and ratio bridge, these are the easiest bridge to design. Okay. Good, great. So, we are going to design a product bridge, and so we have to use capacitor because we cannot use inductor, and therefore, okay, we are going to design or use a product form. Okay. So, now what can we write? from here Z2 is Z1 Z4 by multiplied by Y3, or you can write directly from this. If I call this Z1, Z2, Z3, Z4, we can write directly as Z2 multiplied by Z3 product of opposite arms, same as product of the other two opposite arms Z1, Z4. Now in this case Z1 is R1 and this is R4. Okay. And now we can write Z2 is same as LS RS. So RS plus J omega LS multiplied by Z3. Z3 is this, call this C4 R4 series combination. I may do it in this way, but another point I will mention is that it will be easier if I write it this way, multiplied by Y3. Y3 is 1 over Z3, the admittance of this branch. Now we have seen that admittance is easy to calculate if the elements are in parallel. Okay, but if these two are in series, it is difficult to find the admittance. I mean, we can find, it is not impossible, but it will take 3-4 lines. But if I instead put these two in parallel, then I can write the admittance quite easily. Okay, then I can now write this Y3 is same as this admittance 1 over R4 plus this admittance, which is J omega C4. Okay. And now equate real to real, imaginary to imaginary. So I can write RS from here, real part same as R1 R4 divided this should be R3. This is R3 divided by R, this is also R. 1, 2, okay, let me call this 3, 3, 3, 3, okay, 3, R3, okay. So R1 R4 divided by R3, this part is RS, and J omega LS, imaginary part, we can write here, we have R1 R4 multiplied by J omega C3. So R1 R4 C3, J omega cancels. So you see, once again we can find the balance equation just in 2 lines. Okay, it's so easy. So the trick is either use a product form of a bridge or a ratio form of a bridge, then the balance equation becomes so easy, you can find it in 2 lines. And another trick is that when you are using admittance, like here in product form, use the elements in parallel, then it's easy to write it, express it. And if you are using it in impedance form, then use the elements in series. Okay. So you see how easy these balance equations are to derive. You don't have to do a long 1-page calculation if you design the bridges in this way, product bridge and ratio bridge. Let me conclude this video. We will take more examples in subsequent videos. The idea here is this topic AC bridge is very boring. Often it seems like we have to remember a lot of bridge. No, all bridges are designed keeping the simplicity in mind. If you just design the bridges in either product form or ratio form, they become very easy. We have seen some examples. We will do more practice in following videos in problem solving, and this idea will be clear. Do not memorize, do not remember anything, design your own bridge. then this boring topic will be slightly funny, slightly interesting. Thank you.